And I'm going to show you two different drawings. This one's from Josh. Can you guys see that or no? A little bit, right? You can see why I use marker instead of pencil. Okay. So Josh has a function here. Actually, this is one you probably recognize, or something like, what function does this look a lot like? Y equals what? We had it in class. 1 over x, right? And so we could say for Josh, the limit as x goes to infinity of f of x equals, what would you say? The limit is 0. As I move to the right, this function is approaching 0. And Joe had this one. Can you guys see that? It's a really cool looking function, I think. He actually drew a dotted line. And so this is his, it looks like it's through 1. So for Joe, L is 1. You guys see that? And I don't know what his function is. It's very cool. Do you have a function in mind or no? Okay. It almost looks like a square root and a negative square root, but you could see that his function, as you approach infinity or negative infinity for his function, is getting closer and closer to 1. You guys with me on that? The problem is, mathematicians started not being satisfied with this idea of limit. Because how close do you have to get to be close? And how soon do you have to get close to be close? And they started asking questions like this. Okay? And so what happened is, over the years, people developed a definition of limit which was more precise. And Cauchy is the guy that probably gets the credit for first really putting together what we call, it's actually sometimes called the epsilon delta definition of limit because of this Greek letter epsilon that appears. So I'm going to try and explain that to you today. Okay? And how I started was I said, before we talk about limit of a function, let's just talk about the limit of a sequence. And I wrote a sequence this way, a sub n. And that's not what you guys had last night. Last night on the homework, here, let me grab one. You guys had, wasn't it number 67, right?
Yeah.
I gotta find it. Someone has it here. No, maybe the problem itself. There it is. Oh, yeah. So the book, when the book was talking about sequences, number 67 said, and let me zoom in a little bit so you guys can see a little bit better. 67 was this sequence. It said 2 was the first number, and then 3 over 4, and then 4 over 9, and then 5 over 16. By the way, do you know what the next number is? I don't know if it's easy to see that rule. Yeah, it would. What's the rule?
Increase the numerator by 1, increase the denominator by 1 squared.
By yeah, actually, and what they did was they wrote a rule. They said f of n is always equal to n plus 1 over n squared. So the first term, f of 1, would be 1 plus 1 over 1 squared, which is 2. That's why you got 2. But like Calvin said, you can see that we're increasing the numerators by 1, because that's an n, and we're going to the next square for the denominators. Okay? And the question is, does this have a limit? All right? And by the way, the notation people usually use for sequences is not f of n, it's a sub n. So we'll say a sub 1 is 2. This is a sub 1, this is a sub 2, this is a sub 3. That's very common. You guys will study sequences a lot in Calc 2. But why bring them up now? Because I think it's a really nice way to understand the definition of limit. If you can understand the limit of a sequence, then you can understand the general definition of limit that we've been talking about all chapter. And so I wrote this definition down. Actually, we should read it out loud, and then we'll go from there. So whoever you were just talking to, go ahead and make sure you can read that out loud to each other. And I'm not going to press pause for a little bit because we don't need to record all that. For every epsilon greater than 0, there exists an n such that. And then the way that I do this is I do an if-then statement. A lot of statements in mathematics are of the form if, then. And so I like to teach that now.
I call them methods in computer science.
You call it what?
Methods.
Methods in computer science. Okay. I think it's important. You'll notice that our book, when you look at the homework tonight, kind of reverses things. And there's a reason they do, which I'll explain. But I thought I'd show you this. So if what? You might remember. Little n is bigger than big N, then something cool happens. And what's the cool thing that happens? Absolute value. That's why we studied that. It's a sub n minus L is less than epsilon. That's right. And so I want to draw a picture for you of exactly what's happening. And so I'd like to use that number 67 from last night's homework as my example. So in 67, a sub n, which they also called f of n, was n plus 1 over n squared. Right? And they listed a few of them for me. So what I can do is I can call this the n-axis if I want. 2, 3, 4, 5, right? Did we do 5 terms? I don't know. The first one was 2, and the next one was, I'm forgetting. Oh, we can figure it out, yeah. 3/4. So that's down to here. And the next one was 4/9, which is a little bit less than a half. And the next one was 5/16, which is almost, it's just above a quarter. And so, yeah, I might start to think that my limit is what? 0. And if you understood what I told you about degree yesterday, you know that the limit is 0. But how do we show that the limit is 0 using this definition? Well, the idea is, for any number that's a positive number you can pick, I ought to be able to find a number n such that this is true. Ashton, can I have a small number, please?
0.006.
0.006. That's almost a seal number, right? That's a small number. So if Ashton says we have 0.006, okay, well, then could I draw this inequality? It would be, so what we would have is we would have a sub n minus, what did I say the limit was? 0 is less than 0.006. Do you think we could find, this is kind of what we want, right? We want the absolute value of a sub n to be less than 0.006. Hey, wait a minute. Aren't these terms all positive? I don't care what you plug in for n. Won't they always be positive? Yeah, because we're going to plug in positive numbers only, right? So I guess I don't even need the absolute values. I could just say, I want a sub n to be less than 0.006, because Ashton said that was what our epsilon is going to be. Now, what's the picture? One thing you should understand, guys, is that the barbell is going to be on the y-axis, not the x-axis like I was drawing before. Because my L limit is centered, it's a value on the outputs, the y-axis. Does that make sense? So now what I'm saying is, can we find a number, capital N, so that from there on out, all the a sub n's will be less than 0.006? I bet we could do that. Give me a really big number.
10,000.
10,000. Wow. So let's see what a 10,000 is. A 10,000 would be, well, 10,001 divided by, wow. Well, 10,000, now if I do 4 more zeros, that's 10,000 squared. Thank you. So I have 10,000 divided by 100 million, basically. Is that less than 0.006? I'm going to say yes. You know why? Because I can count decimal places, right? I could cancel out 4 decimal places, 4 decimal places. I still have 1 over 10,000 or so. How did we get n equals 10,000? We just took Wolf. He said, hey, give me a number. Now, notice if capital N equals 10,000, we have this. And also, a sub n plus 1 is smaller than a sub n for all n. I hope that doesn't throw you if I do another upside down a. I'm just tired of writing. In other words, isn't it true that each number is going to be a little bit closer to 0 than the one before it? Well, yeah. This is kind of an obvious problem. But I think that's okay. The point is that if you pick n equals 10,000, we're going to be less than Ashton's epsilon. However, you guys know Calvin as well as I do. We've known him for 2 weeks now. And if I had asked him for a small number, he would have said like 10 to the minus 54 or something like that, right? A real seal number. .1. Would this number, this fraction, be less than his number there? No, because he's trying to be difficult. So, that's okay though. Because what happens is, first you choose epsilon. Does there exist a number, n, which would deal with Calvin's example? Yes. Maybe I can't pick 10,000 anymore. Maybe I need to pick a Google. Ha, got it. Are you with me? What we need for the limit to exist is, for every epsilon, there exists some n such that the condition holds. Such that what condition holds? Such that the rest of the terms are going to end up in what I like to call the epsilon window. And this is really the picture you need to know. Go ahead, Garrett.
What does it say right underneath the note of n equals 10,000? What does that say?
This says a sub 10,000.
Okay.
The 10,000th term equals this.
What's that number on the bottom? Okay.
It's 10,000 squared, so I think it's 100 million,
Okay.
if I did that right. And that's less than 0.006, which is what we wanted. Okay?
What do you think, as long as we can find a number greater than any number or less than the other we think about?
Yeah, you want to be able to make sure that from there on out, the rest of them are good, let's say. So I thought that's sequences, right? But it's funny because we don't study sequences until, well, chapter 10 or something. So it's calculus 2 is when you really start dealing with sequences. So now I want to move on, and I want to do a problem from your book. By the way, quick notice, I changed the homework for today. I changed one problem, so make sure you check it again. If you have a printout, it's going to be wrong. Which one did I change? Oh yeah, I assigned 51 instead of whatever it was, 29 or something like that. And the reason I did is because it really ties into what I just wanted to talk about here. So if I look at the book, maybe we can do number 50. Here. Ah, here it is. Oh, shoot, had it. There it is. The limit at infinity. Let's do problem 50. This is a nice problem. It says, use the definition to prove these following statements. And so the problem 50 says, we want to prove that the limit as x goes to infinity of 10 over x equals 0. By the way, if I just asked you, hey guys, what's that limit? I think you're at the point you would say, oh, the limit is 0. It's kind of like 1 over x. It's just I multiply by 10, but not a big deal. Another thing is that if I asked you to sketch a picture of what's going on here, I'm sure you could do that also. Here, let's plug in some values for x and graph this. If I plug in a 1, I'm at 10. So there's the point 1 comma 10. If I plug in a 2, I'm at 5. I'm halfway there, right? By the time I get out here to 10, I'm finally down to 1. In order to get to a half, I'm really got to go to 20. Right? So there's the point 20 comma 1 half. Are you with me? That's the picture. What do I think the limit is? I'd say the limit is L equals 0. Right? That's the limit. Okay. So here I go. We want to prove this. So we need to show for every epsilon greater than 0, there exists, oh, timeout. Hey, one thing to say here. The first problem I gave you was a sequence. This is not a sequence, this is a function, but it's done almost exactly the same way. Let's look in the book again. They have a definition. It says, the limit at infinity means that for any epsilon greater than 0, good. You guys see it's pretty much the same definition, right? There exists what? Yep, a number n, and it actually says greater than 0, such that. Now, do you notice they used a different word than I did? They didn't use if then. What did they do? They did whenever. Logically, that just switches the if and the then. Okay? So I'm going to use if then again. If, what should I write after my if? Yeah. If x is greater than n, now it's not n anymore because the inputs for a function are x. They could be any number we want. Then what? Absolute value. Yeah, last time it was a sub n minus L, but now we don't have a sequence anymore, so it's going to be f of x minus L is less than epsilon. That's what I need. I think it's helpful to do what I did with Ashton before and Calvin. I'm going to pick a value of epsilon and just do an example. I think before we do the proof, it's helpful to do an example. Suppose epsilon is 1/2 or 0.5, right? If epsilon is 1/2, We're trying to find a number such that if x is bigger than my number, then this will be true. Now, when I say this will be true, remember what it means. There's a barbell. Where's the barbell? On which axis? The y-axis. That's why it says f of x here, right? Because f of x ends up on the y-axis. Centered at L. The center is L. And I want to go up and down 1/2. So say between 1/2 and -1/2. This little window is where I want my outputs to be. If you told me capital N is 2, I'd say no, you're not there yet, because this is 2, 1. If you told me capital N is 10, I'd say no. I'm sorry, this is 2, 5. This is 10, 1. What's a capital N that would work for epsilon is 1/2? 21 would work, sure. Capital N equals, actually 20 would even work because there's a greater than here, right? But N equals 21 works, right? Guys understand? So now what we need to do is how do you show that no matter what you pick for epsilon, there's an N that works? How do we figure that out? Okay, watch. Let epsilon be greater than 0. I don't care what it is. The way you work on proofs is you look at the thing you're trying to conclude, the part after the then. You really look at that. That's what we want. We want, now let's fill in this piece. Absolute value of, now what's my f of x? It's 10 over x, right? Minus 0 to be less than epsilon. Now here's why the book writes whenever. Whenever what happens? X is bigger than what? N. You don't always have to have this true, but if x is bigger than n, like in our example, Joe says, hey, when n is 21, anytime you're past 21, you would be contained in that epsilon window that was defined over here. Does that make sense? So this is what we want to have happen for any epsilon. So we need, let me just simplify this a little bit, the absolute value of 10 over x to be less than epsilon. Right? We need the absolute, we need 10 divided by the absolute value of x to be less than epsilon, because 10 is positive. So the only thing I really need absolute values around is x. Ten is less than epsilon times the absolute value of x. Do you see what I did to both sides? What did I just do? I multiplied by absolute value of x. Is that allowed? Yeah. It's positive, so it doesn't reverse the inequality. So what is it we need? We need absolute value of x. Let's see if you follow this. I'm trying to get it by itself, guys. So what am I going to do to both sides of this inequality? Divide by, not 3, by epsilon, yeah. And so I'll get absolute value of x has to be bigger than, because it's on the bigger side, bigger than what? 10 over epsilon, right? And so here's the trick. Given epsilon greater than 0, we choose capital N to be equal to 10 over epsilon. Then, if x is bigger than capital N, we have absolute value of 10 over x minus 0 is less than epsilon as required. Yeah, and I got to show it to you a little bit more. And I want to talk through it a little bit here. See, you work on the conclusion until you get the absolute value of x by itself. Because then, if we choose capital N to be this positive number, whenever x is bigger than that, I know I could go backwards through the steps and get what I wanted, the conclusion. That's a proof for any value of epsilon. I think one last test that proof works, let's go back to the example we did before. Remember I said let's let epsilon be a half? All right, let's choose n using our little formula. If epsilon was a half, we need the absolute value of x to be bigger than what? 20. 10 over a half is 20. That's why Joe's choice of 21 worked. Do you guys get that? But the point is, it doesn't just work for a half, it works for any epsilon. Take 10 over epsilon and you have it. And that proves that the limit is indeed 0 in a precise manner. Okay? So I want to give you guys my notes on a precise definition of limit. Okay, that's my job today. See if I can help you learn how to understand a precise definition of limit. But what I said first is we want to review absolute value. Okay, so here's a quick review. And so I always like to start with, well, I mean, what I really need to review with you guys is absolute value inequalities, right? So something like absolute value of x minus 2 is greater than or equal to 5. But what I said was, why don't you guys start with the equation? Because really, when you solve an inequality, usually what you do is you solve the equation first, and then you deal with the inequality part. There'll be kind of regions to shade in or something like that, right? So what do you do with x minus 2 equals 5? First of all, how many answers do we expect to get? 2, right? Because we know we get an answer if either x minus 2 equals 5 or if x minus 2 equals negative 5, right? So we know that in either case I have a solution. And so I get x equals 7 or, and I love when an algebra student says x equals negative 7. No, I hate that actually. But x equals negative 3. Okay, so we're ready, right? And now, how do you tackle the inequality? Well, you do it similarly, right? You're going to say there's 2 possibilities. We either have x minus 2 is greater than or equal to 5, or, and do you remember the other one? You do x minus 2. Yeah, now why is it less than or equal to negative 5? That's right. I mean, some of you by now, you just kind of know it from habit. I guess when I teach this, I end up having them, like there's a step before where they do this is greater than or equal to 5, and then you multiply by the negative, and then the inequality switches. But this is what you get, right? And so what do we get as answers here? Well, I guess we get x is bigger than or equal to 7, or x is smaller than or equal to -3. Correct? Okay. And if you had a good algebra teacher, in addition to solving the inequality, they would have you graph the solution on the number line. How many people remember having to do that at some point? I mean, a good algebra teacher would do that. And so let's do that. Let's graph the solution. And so we say, well, here's -3. I'll put a dot there. And here's 7, right? And I'll put a dot there. Or if I'm doing the inequality, here's -3. I put a dot, but what else do I do? Shade to the left, because it says we're allowed to be smaller than -3 as well. So I shade to the left. Or I put a dot at 7, and I shade to the right. And so that represents the complete solution set to that inequality. And then I could say, well, okay, let's do one more. Let's do absolute value of x minus 2 is less than 5. But I claim that if you did the other ones, you know the answer. Right? Because these are all the points that make the absolute value greater than or equal to 5, right? So why don't I just go right to the graph? What would it be? All the points between -3 and 7, right? And we'll put open circles around it because this is what's called an open interval, actually. You don't include the endpoints, okay? You guys with me? Now, to get that set algebraically, notice I did the graph first. You would have to do things like this. You'd have to say x minus 2 is less than 5. You wouldn't write the word or anymore. You would write the word and, or intersection if you want. You need x minus 2 to be less than 5, and you need x minus 2 to be greater than -5. And if you work it out, then you get the intersection of the two rays ends up being this. Okay? So that's what I have so far. If you had a great algebra teacher, they had you do one more step. You see the red barbell that we just drew? I'd like you to find the center of that barbell, or the balancing point. If you're Popeye, you're going to pick it up on your pinky finger and balance it. Where would that be? I'd like you to label that. You can talk to the person next to you to make sure you guys agree. You can check, of course. Once you think you found the balancing point, check how far it is from either endpoint, right? So what's my balancing point? My balancing point right here is 2. And how far is it from either endpoint? Wait a minute. What'd you guys say the balancing point was? The balancing point is, and how far is it from either endpoint? Dun, dun, dun. Coincidence? Are you saying that we were doing that entire worksheet of algebra problems and I didn't have to? Yeah, fine. If you had a great algebra teacher, they would have shown you that. Not so much that they wanted you to avoid all the algebra, but it's that they knew you were going to take calculus. And to understand today's definition, it really helps if you understand that when I write absolute value of x minus 4 is less than 3. Why don't you guys go ahead and draw the graph for that? Go ahead. Won't take you any time at all now. What's the center of this graph? What's the center? 4. Just like 2 was the center of this graph, 4 is the center of that graph. And how far away from 4 do I go? So I either go to 1,
I'll put an open circle there because we're not allowed to be equal to, I notice. Or I go to 7. And so you can do all the algebra if you want, and you will get this answer. This says, how many have heard before that absolute value means distance from 0? Okay? And they're right. Like if I write absolute value of x is less than 2, that means the distance from 0 is less than 2. And you're really talking about, well, from negative 2 to 2. That's a very common problem to show in an algebra class. But we're really talking about a center, and what might you call this distance then? A radius. If you think of this as part of a circle, sometimes that's called the center and the radius. And we'll get to that maybe, well, maybe not actually. Some other class you get to that. Okay? But this is a really powerful idea. And actually, it just reminds me, I was grading the Chapter 1 review that a lot of people worked on. That's a hard set of problems, by the way. Okay? And what I may end up doing is I'll hand them back to you with some corrections and give you one more resubmit is what I'm thinking for those people that worked on it. And if you didn't work on it, don't worry. We'll be learning this algebra, all semester long. But I just remember problem 1E said, can you please graph this set? It said, the set of all x's such that the absolute value of x plus 3 is greater than 4. Well, actually what it said is true or false. Can you graph that without picking up your pencil? That's a good question, I guess. So let's sketch a graph now that we understand how to do it. So what should I make for the center of this graph? It's a little tricky, I guess. I mean, notice that in the previous problems, it was always x minus the center. You see that? So you know what the center is going to be for this problem? It's going to be negative 3 is the center. And this says I want the distance from negative 3 to be larger than 4. So how far away should I go? Well, let me go over to positive 1, right? And let me go over to negative 7. And I claim that if we put anything to the right of positive 1, we'll be in good shape, right? Like if I put in 2, 2 plus 3 is bigger than 4. But also if I go to the right of negative 7, does that work? You guys with me? And so that's what the set looks like. Oh, and so the question was, can you graph this without picking up your pencil? And of course the answer is no, you can't. Okay, but this was 1E from the Chapter 1 review. Okay? How are we doing so far, okay? All right. Now, that's my algebra review. What I'm supposed to do is give you a precise definition of a limit today. Okay? And I'd like to share with you, when I took calculus, I had a very good instructor. And first he asked me who were the inventors of calculus on every test, and it was always Newton and Leibniz. All right. But then the next question that he asked was this. If you have this, the limit as x approaches a of some function, and I tell you that it equals some number, what does that mean? What does that mean? Okay? And here's the definition that we had to spout off. And so I'd like to write it for you. Whoa! Well, I'm using some shorthands here, and I'll translate for you in a minute. You ready? Okay. That is an upside down A. You're right. I didn't lose it. Okay? This is a mathematics shorthand. And what it means is, for every, or for all, you could say. And this is a small Greek letter. Do you guys know what letter that is? No? Epsilon. Epsilon. for every epsilon, well, greater than 0, and then the backwards E stands for something just like the upside down A stands for something. These are just phrases that are used all the time in mathematics. For every epsilon greater than 0, there exists, that's what this backwards E means, there exists, and do you guys know what Greek letter that is? That's delta. Okay, so you got lowercase e and lowercase d basically, but we're using the Greek versions because, I don't know, they ran out of letters and they said, well, let's go to another language. Let's use Greek. Okay, so there exists a delta, again, greater than 0, such that now I'm going to write the next part of this a little differently than the book. Okay? I'm going to write if something happens, then something happens. And the book writes it slightly differently. They use the word whenever. And then they kind of reverse the order. And I'll show you that today too. But here's what they write. Okay? If 0 is less than absolute value of x minus a less than delta. That's too small, guys. I'll write it bigger here so you can see. If 0 is less than absolute value of x minus a is less than delta, then, and what I'm about to do is write down another absolute value inequality. The absolute value of f of x minus L is less than my little epsilon. And that's a big mouthful, I guess, huh? Absolute value of f of x minus L less than epsilon. So this is what we had to write as an answer for the definition of the limit. And then what we had to do usually was try to explain it using some diagrams and using some pictures. But one thing we couldn't do is we couldn't use these really cool applets that your ebook has. And so I thought I'd pull those out and try and explain what's going on. Okay? But before I do that, let me just say one thing here. You guys understand something about, well, hey, take your finger and cover up the 0 for a minute. Forget about that. We'll deal with that in a minute. Okay? But you guys understand something now about this inequality, right? What's the graph of this inequality look like? Just this guy, right here. Well, what's the center? The center is A, right? Now remember, A is some number on the number line. And what is A in the original problem? It's the thing that your inputs are approaching. And we've done that a lot in this course. We've said, hey, let's approach the hole. Even though the hole in the graph isn't defined, let's approach it and see what the limit is. You guys remember that kind of problem? That's what I'm talking about here. So we're approaching some value A, and we want to know what are the outputs approaching. You guys with me? So why get all crazy about this definition? Because what does it mean to approach something? That's what this definition captures. Okay? Again, this inequality says that the center is A, and it says that the distance away from A is less than what? Yeah, this little delta, right? So you have to picture this. Here's A. You're going to move delta away in either direction, all right? And somehow, if I put a little open circle maybe at A plus delta, and another open circle at A minus delta, this is the neighborhood where I'm saying we're living. If we're somewhere in this neighborhood, then Now this is an interesting inequality. This is another absolute value inequality. What's the center of this absolute value inequality? L. But the difference is this. L lives on the y-axis because you see f of x here. So I think it's time to go to the applets, and I can kind of show you how some of this works. Okay? And you saw this in the book last night, but let's take a quick peek. So if I just kind of scoot down here, yeah, here's this word sufficiently close. That's what we're trying to capture today with these absolute values. Now, here's a pretty nice picture. Okay, so this is the solution to example 1. And so down here, notice the inequality here. It says x minus 3 is less than 0.25, right? So 0.25 is which Greek letter here? That's my delta. You guys with me? And what they did was, they moved, I guess, the 3.25 and they moved to 2.75. And they shaded everything in the yellow there. Well, except for 3. And the reason you don't count 3 is this. See how it says absolute value of x minus 3 is greater than 0? You know, that's the part I didn't explain. Right here. This piece. That says, in our new example, that says absolute value of x minus 3 is greater than 0, right? Well, for that to be true, actually, think of it this way. There's only one number that would make this false, because absolute value is almost always positive, right? What's the only thing that is not a solution to this inequality? 3. So when you write that x minus a absolute value is going to be bigger than 0 and smaller than delta, what we're saying is, hey guys, this is the picture, but we're not going to worry about what happens when x equals a. So back to the applet. I'm not going to worry about what happens when x equals 3, but I am going to try to if the x's are somewhere in this neighborhood, let me try to draw this picture. As I said, maybe I'll draw it over here. On the y-axis somewhere, we have what I'm calling the limit, L. And what I'm saying is that's the center, right? Now, how far away from L should I move? Epsilon, whatever that is. So here's L plus epsilon, and here's L minus epsilon. And the game is this. If this is truly the limit, and you pick any of these inputs, we need the outputs to end up being between L minus epsilon and L plus epsilon. And what's really strange about this is the very first part of the definition. What's the very first thing it says? What's that said on Amy? For all, or for any epsilon you can think of. You guys with me? And epsilon is usually going to be a very small number. So let's look back at the applet and see what they picked for epsilon. Just curious. Okay. Well, here. They have 3 choices. You could pick 1, or you can pick a half, or you can pick an 8. And then delta, they have 3 choices. You could pick 2, right? Or you could pick 1. You see that? Now, what they're doing, by the way, what's the limit in this problem? Looks like they're trying to prove that the limit is 5, even though it's not defined there. See, you guys see the hole at 3, 5? They're trying to show me that the limit is 5. And what this definition would mean, if the limit is 5, it would mean that I don't care what you pick for epsilon. You pick epsilon, I'll find a delta so that all of my outputs end up being in the blue picture. Now check this out now. What does my delta equal here? 1. That's a small number, right? And if I take delta equal to 1, all my inputs are between 2 and 4. And it looks like my outputs are between, is that 4.5? And 5.5. So are we in the range between 4 and 6? Yes, we are. Now what if I pick a different epsilon? If I make epsilon equal to 1/2, are all the outputs still in the range? I think so, barely, right? Looks to me like we're going from 4.5 to 5.5. But here's the thing. If I pick epsilon equal to 1/8, now is it true that all the outputs are in the blue range? Not anymore, right? But that's okay. Because all that the definition says, if I go back to the definition, it says, hey, for any epsilon greater than 0, there has to exist a delta greater than 0. You look at the applet again, and you say delta equals 1, that's no good. Because I'll have outputs that are not in what I call the epsilon window. I mean, delta equals 2 is even worse. There's a lot of outputs that don't make it into the window. But if I take a small enough delta, delta equals 1/4. Now does it work? Now are all the outputs are in the epsilon window? Yes, it is. It's true. Yes, it's true. Could I make epsilon smaller? Yes, I could. Then what would you have to do to get it to work? You'd also make delta smaller. That's the game. Given an epsilon, can I find a delta that'll get me in that window? If I can, then the limit exists. Now, if I can't, then we have a different story. Then the limit may not exist. And so we have some examples here like that. All right, so quick check 1. In example 1, find a positive delta satisfying this statement. Oh, I should walk you through this. I think this is worth thinking about here. Okay? So let's go back to example 1 for a minute. So it says, take the graph of a linear function. It says the limit as x approaches 3 of f of x equals 5. I think I'd like to write down exactly what that means. Okay? So here I go. This is example 1 from the book. Here I go. It says limit as x approaches 3 of f of x equals 5. Well, what does that mean? Well, let's use the definition up above. It means for every epsilon greater than 0, there exists delta greater than 0, such that if 0 is less than, now I don't want to write x minus a this time. I want to fill in what I have. What's the a value for this problem? 3. Because remember, a is whatever the limit is approaching. X minus 3 is less than delta, then see if you could fill in the rest. Don't write L. What am I going to write? F of x minus what? 5, less than epsilon. F of x minus 5 is less than epsilon. So now we look at the picture, and it says, okay, can you find a delta satisfying the statement? So they say, what about when epsilon equals 1, and what about epsilon equals 1/2? And again, I guess I don't want to go through this too much. I mean, we just did. If epsilon equals 1, we want to be between 4 and 6. And that was actually shown down here, right? When epsilon equals 1, you want to be between 4 and 6. So we have to, epsilon is 1. So we have to have delta that'll get me there, okay? Now, they're showing you a little bit of algebra in this example, too. No, they're not. They're doing it with the graph, and that's okay. Okay. So we're going to do an example where there's a limit of a linear function. Okay? And it says, prove that the limit as x approaches 4 of this equals 1 using precise definition of a limit. Okay? So you're going to want a new sheet of paper because these take a little time. Okay? And we're going to write down limit x approaches 4 of 4x minus 15 equals 1. And I'll tell you what I'm going to do. The very first thing I'd like to do is write down this. Means, and so now you may have to reference what you just wrote down for notes, right? Because we want to write down what that means, the definition. So what do I do? I say for every epsilon greater than 0, there exists a delta greater than 0, such that and then I write if 0 less than, now what's going to go in the absolute value bars this time? Remember, it's x minus a in the definition. So what am I going to write? X minus 4. There it is. X minus 4 less than delta. Then, now here it's funny because what usually goes in the bars is f of x minus L, right? But I actually know what f of x is. Usually here, I'll say f of x minus L is less than epsilon. But I actually know what the function is. What's the function we're dealing with? This 4x minus 15. So let's put that here. 4x minus 15. That is f of x. Minus, what's the L, the limit that I have? 1 less than epsilon. Okay? Now, again, the game is we need to prove this. Because it says prove that that limit is 1. That means we need to show that for any epsilon at all, you can find a delta to get me in the window. So I want to show you how this works. Okay? So give me a small number for epsilon. What should I use? 0.5. Okay. So I'm going to call this practice. Let epsilon equal 0.5. We need to find a value of delta that, and I'll just put in quote, works. We need to find a value of delta that works. All right, I'll see if I can do that. So what I'm going to do is I'm going to analyze this. And I'm going to say, we want what? Well, we want, if I simplify that, what does that say inside those absolute value bars? Sure, 4x minus 16 to be less than, and I'm going to make this in red because the only reason I'm doing 0.5 is we needed kind of to practice a little bit here. We want 4x minus 16 to be less than 0.5. Right? Now here's where, this is kind of interesting what you do next. I'm going to suggest that we do some factoring here. And factor out and write this as 4 times what? It's x minus 4. So that's what I want. I want 4 times x minus 4 to be less than a half inside the absolute value bars. You guys with me? Hey, and I have a question for you. Isn't this equivalent? Absolute value of 4 times the absolute value of x minus 4. Wouldn't that be the same as the absolute value of 4 times x minus 4? Because if you think about it, all that absolute value does is make sure that the signs are what? Positive, right? Well, what if you have negative numbers? If you multiply 2 negatives, you get positive. If you multiply 2 positives, you get positive. So I think you could be convinced pretty quickly that that's an equivalent statement. This is what we want. Are you with me? So we want this to happen. So check this out. What is it that we really want? We want the absolute value of x minus 4 to be less than 0.5 divided by what? Divided by 4. Okay. Back to the definition. Notice what it says. It says we need to find a delta so that if 0 is less than x minus 4 absolute value less than delta, then this will happen, this thing that I want to have happen. And so the trick is choose delta to equal 0.5 divided by 4. If you do that, it works. If delta is 0.5 over 4, notice now, if 0 is less than x minus 4 is less than delta, less than that, we get absolute value of 4x minus 15 minus 1 less than epsilon by working backwards. What do I mean by that? Well, if we choose delta to be 0.5 over 4, then any time that this is true, we know that this is true. Because that's delta, 0.5 over 4. And now you can work back through the steps, and you'll end up with the thing we wanted. We want any time that this is true, then we get that to be true. And that's an example of a delta epsilon problem. Now, I said this was practice. Let epsilon equal 0.5. Did we ever really use the number 0.5 anywhere special? I guess it was here, right? And it ended up being that the delta we wanted to choose was 0.5 over 4. I need a smaller value of epsilon. So I pick a seal number like what? I don't know. How about 0.0001? All right? So I do that. And now I'm going to draw a sketch. So let's see. You guys, the function that I need to draw is y equals 4x minus 16. That's a beautiful function, right? Y-intercept is negative 16. That's down here somewhere. What's the slope? 4. And what point does it go through? It goes through, according to this picture, it goes through the point 4 comma, I'm sorry, it's 4x minus 15. So it's 4x minus 15. And it goes through 4 comma 1. Right? You guys agree this is my picture? Okay. And then what I need is I need my magic zoom in button. You see that window? I'm going to zoom using today's modern technology. So here's the line. Here's the point, 4 comma 1. Now, Dan picked us a value of delta. Delta, for our first example, was 0.5. And that meant we were considering inputs between what and what? 3.5 over to 4.5. Are you guys with me? Oh, I screwed that up. That's not true. That is not true. 0.5 was not the value of delta. What was 0.5 the value of? Epsilon. Sorry about that. So that meant we want values of epsilon. We want the outputs to be between something and something here, right? If the limit we're saying is 1, what we wanted was the outputs to be between 1.5 and what else? 0.5, right? So they would be within epsilon of 1. And so the game was, could we find a value of delta that would work? So we did a lot of algebra, and we figured out that delta should be 0.5 divided by 4. Yeah, guys, look. This delta I drew, that wouldn't work. Check this out. If I used this delta and put in an input of 4.5, wouldn't I totally miss the epsilon window? That's no good. You can't use 0.5 for the delta. What do I have to use for delta? 0.5 divided by 4. So, I mean, that would be really small from here to here. So let me stay in that black region. If I'm in there, now it looks like the outputs will all be in the epsilon window. Are you guys with me? That's the game. Pick an epsilon, that's what we want, then see if you could find a delta. And if you can always do it, then the limit exists. Okay, now, one more example here. We're going to try epsilon equaling 0.001. No, 0.0001. So check out what the picture would look like now. We want the outputs to be between, I mean, it's really small, 1.0001 and 0.9999. We want all the outputs to be in there. This delta won't work. But is there a delta that would work? I guess. Let's see if that's true, right? Think about, could I go through the same argument? Well, instead of having 0.5, this inequality would say 0.0001, right? And so would this one. And so would this one. So far, nothing's changed much except for that value. And then I would get down here and I would have 0.001 divided by 4, like Mickey said. So what would we choose as our delta? 0.0001 over 4. And if we did that, boy, that'd be tiny. I mean, you'd be like right on 4 almost. And if you're that close to 4, the outputs will be that close to 1. You guys with me? For any epsilon, there has to be a delta that works. Now let's look at the book's argument and see if we can follow it. The book says, hey, we have a equals 4, L equals 1. 4x minus 15 minus 1 less than epsilon. Looks like this. Factor out the 4, divide. But see, they didn't have a value for epsilon. They just said epsilon. That means for any epsilon you have, you can find a delta that works. All you have to do for this problem is divide by 4. Simple enough? Okay. But that's the reasoning behind it. So, let's see if we can follow, well, for example, problem 52. And now, they give me a different definition. The only difference, I guess, is that they're saying the limit as x goes to infinity of f of x equals L. Sorry. Oh no, they say, oh shoot, scrap this. I don't want to do that. Try that again. Let's, for example, do number 51. That's a nice example. 51. Okay, we'll try that again. So in 51, if you look at the directions where it says definition, we have limit as x approaches infinity, f of x equals L means, now really, this is only slightly different than the definition I gave you, right? What's the only change in this statement at all? There's a letter missing. The infinity took the place of what? The A, right? And so we're going to have a problem about where we can't use delta anymore. Because remember that we used to have x minus a is less than delta, right? Well, I don't have a anymore. So I need to somehow do something else with the definition. And so I'll write down what's done, and I'll try and draw a picture and see if that helps you understand. Okay? So what do they say? They say, well, for any epsilon greater than 0, let me do the shorthand. For any epsilon greater than 0. And then they say there exists. What's my shorthand for that? Backwards E, right? There exists, but they don't say delta this time. What do they say? They say capital N greater than 0. And what you're supposed to think of, see, epsilons and deltas are really small numbers. But if they say capital N, you're thinking some big integer. We're going to find a big integer. And then it says, such that, okay? Now notice they're using the word whenever. And that's the opposite of the way I tend to write it. I tend to write if something, then something else. Because to me, hypothesis conclusion is how a lot of people work. But I understand what they're doing too, and we'll see if we can explain that today. So if the input is bigger than capital N, then, and now it says f of x minus L is less than epsilon. In other words, the output is going to be close to L, epsilon close. So I'm going to start with that. And now I'm going to actually work on 51. What does f of x equal in problem 51? Well, they say, oops, I'm missing it. 2x plus 1 over x. Oh, and they say that the limit is 2. You guys would be able to compute that, right? Well, how do you know? Divide top and bottom by x, and it works out, right? You get the leading coefficients. So what we're going to do here is, here's the problem. Let's prove that the limit as x goes to infinity of 2x plus 1 over x equals 2 using the definition. And then I'm going to say, let's draw a sketch. Also draw a sketch. Okay. Ooh, so what does this look like, this thing? Well, one thing you can do is you can start plugging in some values for x. So let me go ahead and use the graphing calculator so I can do this quickly. If I take that out, that'll make this simple. Okay. So I have my graphing calculator ready. And I guess I will plug into my formulas 2x plus 1. Hey, by the way, I'm expecting to get a vertical asymptote for this problem. Where? At 0, right? Because you can't, it's undefined at 0, but if you plug in 0, you get 1 over 0. I'm going to go ahead and graph it. And there's my vertical asymptote at 0. And I'm noticing it sure does look like there might be a horizontal asymptote around 2. Right? And now I'm going to look at the table, and I can actually get some values. I mean, when you plug in something like 5, you're already down to 2.2. And if you plug in something like 10, you're down to 2.1. Okay? So we really are, as I move to the right on the graph, I really am getting closer and closer to 2. So let's draw a sketch. Well, how about I do this? I know that there's an asymptote at 0, and I know that I think there's going to be an asymptote at 2. And some of the values that I just observed, if I plug, I know that there's an asymptote at 0, it comes down. If I plug in a 5, I am at 2.2. If I plug in a 10, I am at 2.1. That's the graph I've seen so far. And then I know there's more over here, right? You guys with me? Okay. I'm going to pick a small value for epsilon. Okay? So let's let epsilon equal 0.1. Is it true that there exists a number so that if x is bigger than the number, I have this happen? Well, let me be more precise about what that would mean. Let's see. F of x see, now you've seen enough that it's time for me to enlarge this so we can use the whole paper. Okay. Let epsilon be 0.1 to start. We want and I'll tell you what I'm going to do this time. I'm going to use the language of the book. You might like this. We want the absolute value, and it says f of x over here. So that's 2x plus 1 over x minus, and what do we want for L? 2. To be less than, well, 0.1 is what I'm saying epsilon is. Whenever, let's use that. That allows us to kind of reverse the order we think about it. We want this to be less than 0.1 whenever x is bigger than some number n. That's what we want. Okay? Now I have some work to do, just like last time. I should do some algebra on this. Do you guys know how to subtract these? Well, how do you write 2 as a fraction? Okay. And in order to subtract fractions, what do I have to do? Okay, so we're going to change that again. And we're going to say that what we really want is 2x plus 1 over x minus, what would I write here instead? 2x over x. And now I can subtract those fractions. So what I'm going to say is we want, well, what would happen when you subtract the fractions? What do you get? We want 1 over x in absolute values to be less than 0.1. Are you guys with me? How do you write 0.1 as a fraction, by the way? 1/10. Well, what do you do next? I claim that what we want is we want absolute value of x to be bigger than 10. Now, how did I get that? Well, a couple ways. Like I said, this is 1/10, right? So what we want really is we want x to be bigger than 10. Okay? It's like you take the reciprocal of both sides, but if you take reciprocals, you have to reverse an inequality. Because like 1/12 is smaller than 1/10, even though 12 is bigger than 10, right? And you could see that this is going to work. What do we choose for n? N equals 10. Now we'll have it. Whenever x is bigger than 10, we will have this, and working backwards, we'll have what we wanted. But the reason I said to sketch a graph is you could see it. Look, this is the limit. What's my limit, we said? 2. Let's draw the epsilon window. 2.1, and then this is 2 minus 1.9. And guys, I am way over time, and I apologize. I'm at 9:28. I'm sorry about that. I totally lost it. But that's what happens when I start doing proofs.